Hello guys, this is CodeNCode and this is a video tutorial for this problem. Bertown Roads rated 2100 taken from Codeforces. This problem is under the category graph and tree. So the problem is we are given n nodes and m bidirectional edges, and we know that one can get from any junction to any another. Basically the graph is connected, so we are given n nodes and m bidirectional edges, and this statement right here tells us that you can reach from any node to any other node, which means the graph is connected. So as there are as ever more dash 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 deal with the your task is to determine whether there is a way to make the traffic one directional, since we know that each of the edges are bidirectional. You can if there is an edge from two nodes u and v, you can move from u to v or v to u. So our task is to determine whether it is possible to make the traffic one directional, that is to make the edge unidirectional, either from u to v or v to u only one directional, so that there is a still possibility to get from any node to any other one. Basically the graph must be connected even after we arrange some direction to the given edges. If we can do that, we have to if the answer is positive, we have to print the possible way to orient the edges. So you are given n number of nodes, m number of edges. Initially the edges are bidirectional, or there is no direction to the edges. But what we have to do, we have to assign the edges some direction, such that even after assigning the direction, the graph is still connected. That is, you can still reach from any node to any other node. Or I should say, after assigning the direction, the graph must be strongly connected. So if we take the example, the first example is 6 node and 7 edges. These are the input edges. So this would be the graph for the input edges. So the answer is 0, because there is no possible way to orient the edges in such a way the graph is still connected. The reason reason is this edge. If I orient this edge towards this from 2 to 4, then no node from this side would be able to get here, or basically there won't be any path from node 4 to 2, or node 5 to 2, or 6 to 2, or from any node from this side 4 5 6 to any node to this side 1 2 3. Or if you assign the edge from 4 to 2 like this way, then what would happen, there is no way from these nodes to reach these nodes. Basically if you orient this edge in any way, then the graph is not strongly connected, or there is no way from some nodes to reach another, and that is not what we want. We want the graph to be connected still, or we want for each node to reach every other node even after orientation. But this is not possible in this case, and hence the answer is 0. Otherwise we would have printed the orientation of the edges. If I had oriented in the answer this edge from 4 to 2, 4 to 2, then I'd print 4 2. Let's take another example. This is the second example with the 6 nodes and 8 edges. These are the edges. If you see, this becomes a graph, right? So what we can do, the output is this, which suggests that if we orient the edges this way, that is 1 2, which means from 1 to 2, 2 3 means from 2 to 3, and 3 1 means from 3 to 1, and so on. If you arrange the edges this way, what would happen, there is a path from every node to every other node. So see, this forms a strongly connected component, so there is a path from each node to every other node, and also you can reach from these nodes to these nodes via this path, or from these node to this node via this path. So you can confirm yourself that in this graph for each node there is path to every other node. So this is a valid configuration. So that is why we have printed this. If you try to solve this problem head on without much thinking, in fact, even if you try to solve this problem may seem a little hard. Even for me when I started to solve this problem. But if you think, first let's take an observation. In this graph we were not able to solve it. We were not able to assign the edges in a way which means the graph is still connected after orientation of the edges. The reason was this edge. Can you think about a property of this edge in a graph? This is a special edge in a graph and we have a special algorithm for this. The edge here is actually a bridge, and the bridge is what causes the problem. If the graph contains a bridge, then if you arrange or orient the graph in one direction, what would happen? The other side of the connected component is not able to reach. If you orient the bridge in this way, then none of the nodes from this connected component would be able to pass the bridge. So that is what makes the problem, or that is what causes the problem. So if the graph contains at even one bridge, then there is no possible way to orient the edges such that the condition follows. So first thing we have to see that the graph does not contain any bridges. And how to do that, I have explained already in my graph theory part 1 series, how to check bridges in the given graph. After that, the problem is how to orient the edges. You can't just simply go and make any node, any edge follow any path, or you can't just take an edge and orient it any way you want. We have to make sure that the edges are oriented in a way that graph is still connected, or still from every node you can reach every other node. So to do that, we will use the concept of DFS tree. Again, the concept of DFS tree I have explained in the same video where I was explaining bridges, because we use DFS tree approach to find bridges. So suppose we can start from the given graph. Since the graph is connected, you can take any node, consider that as root, and start DFS from that. I assume node 3 is the root, and from node 3 I have started DFS. Now since node 1 was not visited, so from node 3 we would make a DFS call to node 1, and this is called the forward edge. Again, everything I have explained in that finding bridge video. Now from node 1 you can reach node 2, so we made DFS call to node 2, and this is nothing special, only DFS. That's all. This is whatever this is happening, this is simply DFS. From node 2 to node 4, this is again a forward edge, and 4 to 5, 5 to 6. That's all. This thing what you have found is a tree, and this tree is called DFS tree because you have found this tree using DFS. There are many properties of this tree, and one of the important properties is that I'll be talking about the properties later, but the fact is, what we can do, we can the forward edges that we have found, we can orient them from parent to child. This was root, so this is a parent, and this node 3 made DFS call to node 1, which means node 1 is child of node 3 in the DFS tree. So what you can do in the DFS tree, you can orient all of the forward edges towards from root to node, or from parent to child. So this is what it looks like if we orient all the forward edges in the similar fashion. And then these are the these are called back edges. So when we reached here, in the adjacency list of 6 there are 2 nodes, 4 and 5, but 5 is its parent, so we won't do anything because we know this edge is a forward edge, so we won't do anything. But 6, there is also an edge from 6 to 4, and 4 is already visited and 4 is not the parent of 6, so this edge is back edge. So what we would do, we would orient all the back edge from child to ancestor. Here what we are doing, in the forward edge we are orienting the edge from parent to child, and for the back edges we are orienting the edges from child to ancestor, from 5 to ancestor, from 3 to node 2 to ancestor. So the claim is, there are 2 claims. First, path from root, there is path from root to every other node. This is the first claim. That is, we started DFS from node 3. So what this says, this says there is path from node 3 to every other node, and this has to be true, and this is easy to understand. Reason, you started DFS from node 3, right, from root, and then you found all of the nodes. So you started DFS from that node and then you reach every other node. Hence there is path from root to every other node. It is easy to understand, nothing too complex about this. So from root to, in this configuration, if we configure the edges this way, then there is path from root to every other node. This claim is easy to make, is easy to understand. Now the second one is a bit complex. It says there is a path from every node to root. Till the claim 1 was from root to you can reach every other node, that is from 3 you can reach every other node, and we know we can reach because we started DFS from that node and found every other node. So there is a path from root to every other node. But the second claim says that from choose every node you can reach from that node to root. Let's take example. From node 1 you can reach 1 2 3, yeah. From 2 you can reach 2 3, yeah. From 4 you can reach because 4 5 3. From 5 you can reach, from 6 you can reach, yeah. So from every node you can reach root, but we can't just take example and say yeah that is true. To understand this, suppose you are on some node, some arbitrary node, then in the DFS tree of that node, DFS subtree of that node, so for node 4 subtree is 4 5 and 6 in the DFS tree. This is the DFS tree complete, and for node 4 this is its subtree. So for any particular node, in the subtree of that node there must be a node who is having a back edge. Back edge means there is a node in the subtree of 4 who is being connected from that node to at least parent of 4. So in the subtree of 4, that is 5 and 6, there is a node which is having a back edge which goes to at least the parent of 4 or above that. So we see node 5 is having a back edge to either parent of 4, which is this, or above that, that is even the earliest ancestor. So yeah, this edge is going to node 3. But how to prove this? The proof is easy. If there is no back edge which goes to at least parent of node 4, then this edge would be a bridge, because this is the property of bridge. This is how we find a bridge using DFS tree. So in the DFS tree, if for a particular node you are checking, if in its subtree there is no node which is having a back edge to at least parent of 4, then if you remove this edge, the whole subtree gets removed or the whole subtree gets disconnected. But since in this graph there is no bridge, because that is why if there was a bridge we would not be printing the solutions, right? We won't be orienting the edges. But since the graph doesn't contain any bridge, hence in the subtree of 4 there must be a a node which would be connecting it to at least parent of node 4. Hence, using that back edge, you can what you can do, you can first go down to that node, and then using that back edge to go up in the DFS tree, and hence you can reach at least one node above, one what we say, one height above from the current height. So same argument would apply to that node, that in the subtree of that node there must be a node which is having a back edge to at least parent of it. If not, then this edge would be uh, a bridge. But since this edge is not a bridge, hence there must be a node in the subtree of this node which would be having a back edge to at least parent of node 2. So you can, what you can do, you can take a path from that node, from 2 to that node, and then take that back edge, so you would reach at least one height above, and recursively doing that you would be able to reach root. So this way we prove claim 2 as well. So so the question is, how claim 1 and claim 2 make sure that the graph is still connected, that is, there is path from every node to every other node. You can easily prove this fact. Suppose you want to prove that there is a path from u to v. So what you can do, you can break this path from u to 1 and 1 to v. U to 1, that is, there is u to 3 and 3 to v. Why? Since 3 is root, so claim 2 says that from every node there is a path to root. That means a path from u to 3 would exist, right? So every path uv you can break into u to 3, 3 to v, or u to root, root to v, because claim 2 says that there is a path from u to every node to root, so u to 3 would exist. Claim 1 says that there is a path from root to every other node, so 3 to v would exist. So every path can be broken down into into this way. Every path uv can be broken down into this way, u to root and root to v. And claim 1 and claim 2 suggests that this path would always exist, and hence using this configuration the graph would still be connected. So all we have to do is, if we find in the if we find a forward edge uv, where u is the parent and v is the child, we would print uv. uv means orient the edge from u to v, right? Whenever we find back edge from a node to its ancestor, remember this edge is also in the adjacency list of 3, but for 3 it would be from ancestor to descendant. When we find the edge which is back edge but from ancestor to descendant, then we won't print it. We would print it when we find the same edge in the descendant and it connects it to its ancestor. Then we would print from that node, that is descendant to ancestor. So how we would do this? First let's see the, yeah, there are 10 to the 5 number of nodes in total. So let me, this should be visible to you guys. Okay, just a second. There is a header file I need to include. Okay, so now since there are 10 to the 5 number of nodes, so we need adjacency list of size 10 to the 5, and there are many other things that we need. Since we are going to test for the bridges, so we need in time, out time, visited, and other arrays. So we need in time array, low time array, visited array. I think that's all we need, and also a timer. This is a simple integer which would keep the time. So we would be having n number of nodes, number of edges, a and b. So n m, and then since the graph initially is bidirectional, so in the adjacency list of A we would insert B. Just a second, I don't know why this happened, why this lags. Okay, in the adjacency list of, oh well, I was in this in my dev. In the adjacency list of A we are inserting B, and then in the adjacency list of B, in this adjacency list of B we would insert A. Now the graph is completed. What we would do, we would make a DFS call, assuming node 1 is what we say, node 1 is the root, and this is the parent of root. Since root doesn't have a parent, that is why we are passing -1. So I DFS current node parent, and this is the parent. So when we reach a DFS, what we do, we mark the current node as visited, and we initialize the in time of current node to be equal to load time of current node. I have already explained this in time out time thing in finding bridge videos, so go and check out the graph theory part 1 series. There you would find 2 videos explaining, first explaining DFS tree, then second explaining how to find bridges using DFS tree. And do not escape the video explaining the DFS tree, because that is the most important videos, I believe, because that is a video that would explain how to find not only bridges but also the articulation point. So just don't miss that video. So after doing this, we traverse in the adjacency list of current node, and there are 3 possibilities. First, this node is actually parent, so we would do nothing, simply continue, because that means you are on this node and you started to traverse its adjacency list, and first node you find is 1. You can't do this, you can't do anything about this, because 1 is your parent and this edge has already been traversed. So we are only inserted for a node either in forward edges or back edges. This is neither forward edge nor back edge, that is why we simply continue. We have nothing to do. But if the current node is visited, or if the current child is visited, that means you are on this node and then you find this edge. You are on this node and you find a node which is already visited. It means it have to be its ancestor, and since it is its ancestor, so what we would do, we would simply minimize the load time. Load time of current node is equals to minimum of load time of current node comma in time of that node, that's your in time of child. I'm calling this child, but actually this is ancestor. This, in fact, this can be anything, either child or either ancestor or descendant. And if the node is not visited, which means this is the forward edge. So yeah, one more thing. Okay, the graph must not contain any what we say, the graph must not contain any bridges. Okay, and then we must print the orientation. So let's take a bool variable. Bool has bridge. Since I am declaring it outside anything, or this is global variable, so it would be initialized with 0, which means false, which means the graph doesn't have a bridge. So and let's create a vector of pair to save the edges. Int. So as in the vector of int you can store integer, vector of pair would store pairs. So this would be the edge list. The edge that we have to print. Basically, I would be storing these edges at the end to print. So first of all, how to find the bridge? What we do, when we find a forward edge, we make a DFS call to that node, passing the current node as its parent, and after that we check whether this forward edge, because I have explained already, only the forward edges are the ones which can be bridges. So after making a DFS call, we check whether this is a bridge or not. For that, if low time of child is greater than the in time of current node, if that happens, then this edge, uh, this node to child edge is actually a bridge. If this happens, then has bridge is equals to true, and after that simply return, because we don't have to continue the algorithm anymore. We can simply return. So since we have found the bridge, so if we have found the bridge, then the graph, the result is going to be 0. That is why has bridge, I'm making it true. Otherwise, if we are reaching this place, which means we haven't returned, which means this edge is not a what we say, not a bridge but a forward edge. Since this is a forward edge from node to child, right? So that is why in the edge list, push back, I will insert a pair which is node child. So what it means is that you are currently on this node, and after completing the DFS of this node, you are checking whether this is a back edge or not, this is a bridge or not. Since this is not a bridge, so the edge node child, we would orient this from node to child. That is what I'm doing here. I'm saving it as node child, which means the orientation is from node to child. So this was a forward edge, so I have inserted it into my edge list. So I have inserted it into my edge list. So finally I would print all of the edges if the graph doesn't contain any bridge. And after checking the bridge, what we do, we also minimize the low time of current node by low time of its child. Low time of current node and low time of child. And one more thing here, we this is a back edge, right? When this is a back edge, so what we have to do, this edge, you can be either on node 3 or node 2, but we have to orient it from 2 to 3. So we would orient it when we are the descendant, and we are being when the current node is descendant and the child is actually the ancestor. So what that means, that current node, this is actually descendant, and the child, this node, this is actually your ancestor. So we would print, we would save it, or we would orient it from current node to ancestor, current node to child. So for that we have to check whether we are descendant or not. So if that you can check using in time. In the DFS tree, if you have the higher in time, that means you are descendant than the other one. So this would get 0 in time, this would get 1 in time, this would get 2 in time. So you see 0 and 1, these two are its ancestors, because this is having in time 2. So to check whether whether the current node is descendant or not, its in time would be higher than the in time of child. If that's the case, then the current node is actually descendant and this is ancestor. So and that is what we want. We want the current node to be descendant, we want the current node to be descendant, and we want the child to be ancestor, and then we would print from current node to child, that edge. So if that's true, then in the edge list, we would insert pair node child, indicating this should be orientation of this package. And that's all in this. So after making DFS call, we would check. So after the DFS call is completed, we would check whether has bridge. If has bridge is true, which means there is a bridge, and hence all we have to do is print 0. Otherwise we would print every edge in the correct orientation. Since you can print the edges in it is important to see whether we can print any edge anytime, or we have to print in the same manner as they are present in the input. So you can print the roads in any order. If there you can print the roads in any order. If there are several solutions, print any of them. Yeah, so we can print edges in any order. So I can print it any order. That means I can simply take E in the adjacency list of in the edge list. We are taking edge one by one, and we are printing cout E dot first, E dot second, and L. Believe me, if this gets any error, I do not know how much time it would take to be debugged. Okay, so this is very rare that the program compiles in the very first time. Okay, so let's try. This is the solution. 3.5 was the last. So 3.5, what we are saying, it should be 3.1. let's simply go here. So what it says, 3.5 was the last. So this one says 3, there should be edge from 3 to 1. As you can see, yeah, there is an edge from 3 to 1, and then 6 to 5. 6 to 5, if you are making 6 to 5, then DFS tree must be different. Let's simply submit this and get the answer, because the answer is different from this one, because there can be many different DFS tree. So the program that we have written may be following some different DFS tree, because there are many DFS traversal for a given graph. So that is completely okay for the program to return a different solution that we have seen in this slide. So let's go and simply submit, and that would itself, oh yeah, let us also test for the condition where the answer is 0. At least that would be this is the test case for which answer should be 0. Answer is 0. Okay, at least we are checking bridges correctly. So okay, let's submit. This is running. Okay, which means the program is correct. Most likely this is done. So this was how we solve this problem. So what we did, we extended the concept of DFS tree, and believe me, this concept of DFS tree helps a lot in thinking the solution of a problem of which initially seems very complex. So what you can do, you can simply you can convert the graph into a DFS tree and think in terms of tree, which of course reduces the complexity at a greater level. So what we did, we created the DFS tree, and we claim that there is a path from root to every node, and there is a path from every node to root, and we prove this fact. And then we can see that there is a path from every node u to v, because this path you can break down in u to root and root to v. And that is what we did, and that is how we got AC for this problem, which was rated 2100. So this was all for this lecture, and thank you guys for watching, and till the next video drops, keep coding. Thank you.